can be calculated, can be written down. There are three processes. So there are three transition process that takes place while now we can calculate the rate of this process. The spontaneous emission as shown in the figure A, and adjacent process shown in the middle of the figure, and the stimulated emission is shown in the figure 3 at the right hand side. Now the spontaneous emission means let the two level system as we described. So there are N1 number of atoms per unit volume in the energy E1 and N2 number of atoms in the energy E2 per unit volume. Now, because of some thermal reason, some atoms will be excited to the level 2. Usually they will be in the ground state, but because of some other, any reason, like they get the energy from outside, it can be atoms might get excited spontaneously to the level 2, and then they will come down. This is a normal process, like if you throw a ball towards the top, because of the gravitations, and then it comes down. So the atoms, when are excited to the level 2, they remain there for some time. Usually the typical value of the lifetime, the upper level in ordinary system of atoms, not in case of the laser, 10 nanosecond or less than that. So the lifetime of the level 2 will be less than 10 nanosecond if it is ordinary material, like that where the ordinary light emits from those materials which emits ordinary light, the excited state lifetime is less than 10 nanosecond typically. So the atoms will remain in the level 2 for about 10 nanosecond, and then they will come down. And as a result, the difference in energy comes out in the form of radiation, and this process is called spontaneous emission process. And the rate of these transitions obviously will depend on the number of atoms in the level 2 and a probability for these transitions. So the rate of spontaneous transitions depends on the number of atoms in the level 2 is proportional to the number of atoms in the level 2, and there is a proportionality constant A21, which is Einstein's A coefficient, which is the probability for the spontaneous transition between the level 2 and 1. So it's written as A21. Now, when we incident radiation, external radiations to the system of atoms, these radiations might be absorbed by the material which are in the ground state. Like I am discussing the topic to you, I am sure that many of you will be able to grasp, and your knowledge level will be enhanced. So that is the case, like the radiation incident to the system of atoms absorbs the photon incident and then get excited to the level 2. As a result, the incident photon is absorbed by the material. Incident radiation is absorbed by the material. And the rate of this adjustment process obviously depends on the number of atoms in the level 1. More the atoms in the level 1, more is the probability that this photon will be absorbed. And also depends on the energy density of the incident radiation, that is U omega, energy per unit volume per unit frequency, energy density of the incident radiation, and a proportional B1 to Einstein B coefficient, which is basically again depends on the probability for the absorption between the level 1 and 2. So B1, 2. So the rate of absorption is N1 U omega B1, 2. So this many transitions takes place per unit time per unit volume. This many absorption transition takes place per unit time per unit volume. Now this incident photon might stimulate an atom which are already in the upper energy level to come down, and as a result the two photons are emitted. This is something like the forced vibration. It's something like the forced vibration. As you know, we have studied in 10 plus 1 that every system has some intrinsic frequency. Now, if the external frequency, if you apply an external force with a variable frequency, and if the frequency of that external force matches with the intrinsic frequency of the system, then there is a resonance and the system vibrates with a larger amplitude. So it is forced vibration. Similar here, like if incident a photon, if there is a possibility, in the possibility of the forced vibration, then this photon forces the atom in the upper energy level to come down, and as a result of this process, there is a release of another photon, which is of the same characteristics, means same phase, frequency, polarization, all the same, and so we got the two number of photons starting from 1. And these two photons can further stimulate another 2 atoms to come down, and we have a 4. In this way, the multiplications of the photon takes place by stimulated emission process. The multiplication of the photon is possible by stimulated emission. The laser means light amplification by. So if stimulated emission process dominates, then we can get the coherent photons. So these two photons are of exactly same phase, frequency, polarization, so they are coherent with respect to each other. So the rate of stimulated emission obviously depends on the number of atoms in the upper energy level, energy density of the incident radiation, and the proportionality constant, that is the probability for stimulated emission between 2 and 1, so that is B21 Einstein B coefficient. So RST, that is rate of stimulated transitions, the number of stimulated transitions per unit time per unit volume, is equal to the N2 E omega B21. So these are the three transition process place while interactions of radiations with a system of atoms.
Sir.
Yes, I am hearing. Continue.
Sir, please explain the third stimulated emission once again. How it's multiplied.
Okay, no worries. So as I told that when there is a radiation incident in a system of atoms, then Einstein says that there are three processes. Before Einstein, it was known that these two processes will take place, the spontaneous emission and absorption. Einstein showed mathematical argument, theoretical calculations, that these two processes alone cannot lead to the equilibrium. So to introduce the third process of stimulated emission. Now what is that? Now in case of this case, in the third case, when a photon of frequency omega with energy density u omega incident to the system, this photon might stimulate an atom which are already in the upper energy level. This atom has reached to the upper energy level by any means, for example by absorption, it has reached to the level 2, or by thermal reason it has went up to the level 2. So there are some atoms in the level 2. Then incident photon might stimulate the atom in the level 2 and turn it to the level 1. Incident photon stimulate the atom in the level 2. For example, that I am taking a class and I gave some preliminary discussions on the topic, and then I ask a question in the topic which I have discussed already. So at first I raised your level of knowledge, level of understanding, and then I ask you to answer the questions the way I explained already. So my questions stimulate you to answer in the same way as the way I taught. So it is something like that. So there is an atom which is in the upper energy level, and the incident photon stimulate the atom in the upper energy level to come down. So because of this, there is emission of a photon, and other than the incident one, there is incident photon is present, and this photon stimulate this atom to come down, and there is a release of another photon. Difference between the level 2 and 1, and we got two photons which are exactly the same phase, polarization and directions of propagations, all are the similar, so we get coherent photons. So that is called the process of stimulated emission, because the emission of the photon takes place by the stimulus of an external photon, and the emitted photon are exactly the same character as that of the incident one. So by this you get from one photon to the two photon. Now these two photons may further stimulate to another atom. These two photons may further stimulate to another two atoms which are in the excited state, and they may force these two atoms to come down the down state, and we have emission of another two photon. We have emission of another two and the incident two. So we got four photons of exactly same phase character. So from 1 to 4, and in this way there is amplification. Like if the light passes through back and forth, and then there can be amplifications of the photon possible by stimulated emission. Is it clear? Oh.
Yes, sir. Yes, sir. Now clear.
Yeah. So I think I'll be discussing further. It will be more clearer even little
Sir,
later.
in the third case, why, like in the stimulated emission, when the photon is incident on the N2 photon, like why will it always come back to the lower state? It can also go to the higher state with the energy it gained.
Yeah, you are right. So there is that if you have energy level above level 2, the atom might, you are right, that atom might get stimulated to the upper energy level. That's always possible. But this depends on the phase. Okay, there are further requirements. This is a quantum mechanical process. So, but anyway, so it depends on the phase, and also your material. I have already told that the material is a two-level system. So there are two energy levels exist in the material only, the level 1 and level 2. So there is no existence of any higher energy level here.
Okay.
It is possible. It really happens in many cases. You are right. It really happens in many cases. Like I gave a mechanical example. For example, I was discussing the topic, and then I ask a question. So this is also a stimulus. I gave external stimulus that you answer. So this question, yeah, according to you, this question might create a new knowledge on you. But I have asked the question in such a way that you respond to my question the way I have explained. So that means that you stimulate, and I stimulate you, and you give answer, and that leads to generation of some photon. Like you give the answer, I stimulate you, and you give the answer. So it is something like that. So it depends on the phase. There is some other factors. Definitely, it's not always whether it will be absorptive transitions, or in that case it has to be absorptive. Okay, it's called excited state absorption. There is a possibility, and that is called ESA, excited state absorption. That is possible, that the incident photon is absorbed by the atom in the excited state. But I need to have a possibility of excited state absorption. But if the material is such that the excited state absorption cross section is then there will not be any excited state absorption. Like here, initially we have assumed that we have a two-level system. So you have a two energy levels exist, only level 1 or level 2. Okay, is it clear, Deep?
Yes, sir. And sir, one more question. Like in the spontaneous emission, excited atom in the N2 level will come back to N1 level emitting H nu energy photon. But what if the excited photon in N2 was also stimulated by some photon which is incident on it? So when it comes back to the N1 state, what kind of emission we will call it?
Which state?
So like in the N2 state, the electron already is in excited state, which will try to come back as in spontaneous emission. But what if the excited electron, we also provide some external photon is also incident on it? So will it be stimulated emission that time or spontaneous emission?
Yeah, okay. So I understand maybe you are asking like, what are the other causes that when it will be stimulated, when it will be spontaneous? That is your question?
Yes, sir, kind of.
Yeah, I'm actually, I'll be discussing that in the next. Okay. So under what condition the stimulated emissions will be dominant? Okay.
Okay,
I'll be discussing those. Just wait for a few moments. You'll get your answer. So these are the three basic processes. There are the possibilities. I am telling you these are three possibilities. Now Now we want to get a laser, we want stimulated emission. Now what is the necessity, what is the requirement to have a stimulated emission dominant? Because we want that. We want stimulated emission because we want the photons to be coherent. That is the case for the laser radiation. Now your question is very good, that under what situations it will be spontaneous and under what situation it will be stimulated. Yeah, so the condition for that we'll be looking for, and we'll be discussing that in details. That is the important part of this discussion. So let me tell you that these are the three processes that will take place. Let me repeat once again these three processes. That the rate of the spontaneous emission, the rate of spontaneous emission is N2A21, rate of absorption is N1 E omega B12, rate of stimulated emission will be R stimulated, it will be N2 E omega B21. So please remember the three equations. Now moving on, we are interested to calculate the two quantities. So these are the two quantities that we will be interested to calculate. One is the ratio R1, that is rate of spontaneous transition by rate of stimulated emission, because we want that the stimulated transition should be larger. And then we calculate another ratio R2, that is rate of stimulated emission by rate of absorption. Here also you want that stimulated emission should be dominant over absorption. So we want that R2 should be greater than 1 and R1 should be less than 1, that we want. Now let us see what happens. The thermal equilibrium conditions. Now what is the meaning of the equilibrium? In case of the equilibrium, it has to satisfy the total rate of downward transitions of the atom per unit volume should be equal to the total rate of upward transition of the atom per unit volume, because we are not able to create atoms. Now please remember, I am using the term atom. I am saying atom, it does not mean it will be always atomic transition. It can be electronic transitions, it can be molecular transitions, it can be atomic transitions, it can be group of molecular transitions. Okay, so depending upon that, the type of the material used for laser, there can be different type of transitions. So the term atom to signify atom, molecule, ion, electron, and group of atom, group of molecules, group of ions, and so on, as applicable. But always I cannot say like that atom, molecule, ion. So I'm just using the term atom to mean that. So please remember that. So the total rate of downward transitions of the atom per unit volume should be equal to total rate of upward transitions of the atom per unit volume, because we are not able to create any new atoms, neither atoms are destroyed. So atoms will be either in the or in the upper energy level. So for equilibrium, total rate of downward transitions of the atom per unit volume must be equal to total rate of upward transitions of the atom. So that's essential requirement. So you see, in this case, the spontaneous transition, there is a downward transitions of the atom takes place. In case of the stimulated emission, there is a downward transitions of the atom takes place. In case of the spontaneous emission, there is a downward transitions of the atom. In case of the stimulated emission, there is a downward transitions of the atom. So total rate of downward transitions of the atom is N2A21 plus N2B21 U omega. This must be equal to total rate of upward transition. Now upward transitions of the atom takes place only in the case of absorption. So that is N1 U omega B12, N1 U omega B12. So under equilibrium condition, these two sides should be equal. Now then if you rearrange, you get U omega is equal to N2A21 by N1 B12 minus N2 B21. Or we can write dividing denominator and numerator by N2 B21, we get this is equal to N2 A21 by B21, N2 A21 by N2 B21 divided by N1 by N2 B12 by B21 minus 1. And then N2 cancel out, so we got U omega is equal to A21 by B21 divided by B12 by B21 and N1 by N2 minus 1. Now this is the expression of the energy density of the radiation as per Einstein calculations. Einstein did it in 1917. Now before 1917, the Max Planck has already given his radiation formula, which describes the energy density of the radiation. So in science, discover something new theory that should be, you know, that should explain, that should be able to explain the earlier one, which is already verified by the experiment. That should be compatible with the earlier one, which is already verified by the experiment. Otherwise, people will not believe. So that's the law. So the equation 2, which gives the expression of the energy density of the radiation, must be compatible with the Planck's radiation formula, because Planck radiation formula is already verified by experiment before Einstein's work. What is Planck radiation formula? You have studied it in the black body radiation theory when you have studied that any sub objects when it emits radiations, the energy density of the emitted radiations lying in the frequency range nu to nu plus d nu is u nu d nu is equal to 8 pi h nu cube by c cube 1 by to the power h nu by kt minus 1 into d nu. So this is called the Planck radiation formula. Now we need to replace nu with omega to compare with the equation 2, and here Planck radiation formula is valid for, the radiation in vacuum. So why the speed of the electromagnetic radiation is c. But in case of the laser, your laser emissions will take place within a material medium. So it will have a refractive index other than 1. So the c, the speed of the light, has to be replaced by c by n, where n is the refractive index of the material. So to just to make equation 3 applicable for the case of the laser emissions, we have to replace c by n. So it will be 8 pi h nu cube n cube by c cube 1 by to the power h nu by kt minus 1 omega. So total energy within the frequency range omega plus d omega is e omega d omega. That should be equal to e nu d nu. So and then writing omega is equal to 2 pi nu, d omega will be 2 pi d nu, and then this equation is like this. So u omega from the Planck radiation formula become u omega is equal to h cross omega cube, h by 2 pi is h cross omega cube by pi square c cube, 1 pi will cancel out, so it will be pi square c cube, and NO cube should be multiplied here. The refractive index cube should be multiplied for case of the laser, and then 1 by to the power h cross omega by kt minus 1. So this is the Planck law. This is the Planck's law. Now the equation 4 and 2 should be compatible. And before that, the value of n1 by n2. Now the populations are given by the Boltzmann law. There are three statistical distribution in physics. The one is called the Boltzmann statistics or Maxwell-Boltzmann statistics, called MB statistics, and there are other two, Fermi-Dirac or FD, and Bose-Einstein or BE statistics. Bose is an Indian scientist. You know the story. You might be knowing that he developed statistics, and then his research paper was sent to the Einstein, and then Einstein extended a bit, and then this was published as Bose-Einstein statistics. So that is the BE statistics. So there are available. One is the Maxwell-Boltzmann, and the Bose-Einstein, and the Fermi-Dirac. Now here the Boltzmann statistics will be applicable, and according to the Boltzmann law, the number of atoms in any energy level is given by this equation. It's called the exponential distribution law. Nn is equal to n0 to the power minus En by kt. So you have to remember this equation. According to the Boltzmann distribution law, the populations of different energy level is distributed following the equation 5. Nn is equal to n0 to the power minus En by kt. So if you plot it in a graph, this looks like this. The number of atoms in the different energy level for any positive value of the for say t greater than 0, population, if we plot Nn as a function of the En, then it goes like this. As you go on increasing energy, the population is decreasing exponentially with energy. So this is sometimes called exponential distribution law. This is called exponential distribution law because the populations decay exponentially. Population follow the exponential distribution. So as we go to the higher energy level, you can see that the number of atoms is lower. If you go to the higher energy level, say this is a energy level E1, so the number of atoms is N1, and this is energy level E2, number of atoms is N2, which is less than N1. So N2 is less than N1. So according to the Boltzmann distribution law, the upper energy level will always have a lower population than the lower. Anyway, so by using these equations, you can calculate a quantity called the relative population ratio RPR, that is N2 by N1. That is N0 to the power minus E2 by KT by N0 to the power minus E1 by KT. So it's become E to the power minus E2 minus E1 by KT. Now E2 minus E1 is H cross omega. So if you substitute, it become E to the power RPR is equal to E to the power minus H cross omega by KT. Now if I substitute the value of N1 by N2, then it will be inverse of this. So E to the power H cross omega by KT. So equation 2 become U omega is equal to A21 by B21 E to the power H cross omega by KT B12 by B21 minus 1. 7 and this equation 4 must be compatible. 4 and 7 must be compatible. So if you compare 4 with the 7, then you find that A21 by B21 is equal to H cross omega cube by pi square C cube, and B12 must be equal to B21. So this gives a significant outcome. This gives a significant outcome that the probability for the absorption and the probability for the stimulated emission is the same. Probability for the stimulated emission and probability for the absorptions are the same, and the ratio of the probability for the spontaneous transition divided by probability for the stimulated transition is equal to H cross omega cube by pi square C cube. So these relations are important. These relations to calculate the two ratio R1 and R2 as we have defined little earlier. R1 is the rate of spontaneous emission by rate of stimulated emission. R2 is the rate of stimulated emission by rate of absorption. By calculating these two ratio, we will be able to answer the question that why in case of the ordinary materials we do not get laser-like photon, because Einstein says that it happens with every system of atoms. So even in a lamp which you are using, there definitely then there should be stimulated emission in that. But then why don't we get coherent photons? To get the answer of this question, we have to calculate these two ratio. Now let us first calculate the ratio R1. That is the rate of spontaneous emission, that is N2 A21 by rate of stimulated emission, that is N2 U omega B21. So it's become A21 by B21 1 by U omega. Substitute the value of A21 by B21, that is H cross omega cube by pi square C cube, and U omega is H cross omega cube by pi square C cube 1 by to the power H cross omega by KT minus 1. Just now we have derived here. U omega is this. U omega is this. A21 by B21 is H cross omega cube by pi square C cube, or it is this, and then H cross omega cube by pi square C cube 1 by to the power H cross omega by KT minus 1. So if you substitute 4 here, and then we got this, and then ultimately if you do the calculations, it becomes R1 become to the power H cross omega by KT minus 1. Now we will solve one problem, then we will try to understand that why ordinary materials do not emit spontaneous stimulated photons. So we calculate the value of R1, the real value of R1. That let us calculate R2, the expression for the R2. So R2 is the rate of stimulated emission, that is N2 U omega B21, and rate of absorption, that is N1 U omega B12. Now B21 is equal to B12, and so this become N2 by N1. So R2 become N2 by N1. Just if you follow this diagram, then you can easily understand that R2 is less than 1 in ordinary systems. N2 is less than N1, so R2 is always less than 1. So we got these two quantity. Now let us solve one problem, and then we can understand what happens in a system of atoms, ordinary light source, for example. So consider the problem 2, that an ordinary source of light which is emitting light of wavelength 600 nanometer, and it's working at a temperature say 800 Kelvin. Then find the value of E2 minus U1, that's very simple, and then calculate R1 and R2. And then you write your comment on the result obtained in B and C. Also find the range of omega for which R1 will be much greater than 1. So the first case, you have a two energy levels which are emitting wavelength 600 nanometer. Then that means the energy difference between these two levels has to be H nu or H cross omega, that is E2 minus U1, that is Hc by lambda. So E2 minus U1 is Hc by lambda, and that is H is a Planck constant. In that day interview, the many of you unit of the Planck constants, I was really disheartened. Planck constant is joule second, 6.63 in 10 to the power minus 34 joule second. Please remember henceforth the unit of the Planck constant is joule second, and C is 3 into 10 to the power 8 meter per second, and lambda is 600 nanometer. 1 nanometer is 10 to the power minus 9, so it is 610 to the power minus 9. Then if you calculate, it comes out to be 3.3125 10 to the minus 19 joule. Now we like to write in electron volt unit because energy is an electron volt unit for the electrons. So to do that, we have to divide it 1.6 into the power minus 19. Then you get this much electron volt. So ultimately it become 2.1 electron volt. So in ordinary light, which emitting a red color light of around 600 nanometer, the energy level difference should be of the order of 2 electron volt, 2.1 electron volt. Now calculate RO1, that is the rate of spontaneous emission by rate of stimulated emission, that is e to the power h cross omega by kt. So e to the power e2 minus e1 by kt minus 1. E2 minus E1 we have already calculated 3.3125 10 to the power minus 19 joule, and K is the Boltzmann constant 1.38 into the power minus 23 joule per Kelvin. Please remember these quantities because these will not be provided in the examinations. Kv is 1.3 10 to the minus 23 joule per Kelvin, and T is the temperature in Kelvin, that is 800. Now if you substitute and do the calculations, you must do the calculation by yourself, otherwise you will be forgetting. So calculations are although done here, but you must do at your own hand. So it comes out to be of the order of e to the power 30, and the value of E is nearly 3, 2.7. So 3 to the power 30, you can understand, is a very large quantity. So R1 is very much in ordinary system of atom. What is R1? R1 is the rate of spontaneous emission. R1 is RSP divided by rate of stimulated emission. So RSP divided by RST. So the rate of spontaneous emission, stimulated emission, which is much greater than 1. So what you understand from here, that the spontaneous emission will be predominant over the stimulated emission. Okay, so although in ordinary system of atom there might be few stimulated transitions, if happens at all, number is very less. So ultimately the characteristics of the photons which are emitted from ordinary light will be dominantly led by the spontaneous emission character. So that's why in ordinary material you do not get spontaneous photons, stimulated photons. The photons what are emitted are random in phase, frequency and polarization. Now calculate R2. Again R2 will be to the power minus 30, so it is much less than 1. So you understand the stimulated emissions will be R2 is the RST by R absorption. So it will be much less than the absorption. So your stimulated emission process will not be dominant in case of ordinary system of atoms. Now we can calculate a frequency for which spontaneous R1 will be much greater than 1. So there is a cutoff frequency that is omega cutoff is kVt by h cross. We can calculate e to the power h cross omega by kt minus 1 was this. R1 was e to the power h cross omega by kt minus 1. So this will be much greater than 1 when this quantity is much greater than 1, like e to the power x. When x is much greater than 1, then e to the power x is much greater than 1. So when h cross greater than 1 or omega greater than kVt by h cross, so you can calculate a cutoff frequency. So that is like this, all the calculations are done. So I don't want to go all the steps. So today I will be stopping here because we are already near the end of the time, and but maybe 2-3 minutes. So these are the real situations what happens in ordinary system of atoms. So we understand we have to do something else to achieve dominant stimulated emission. So that we'll be discussing in the next class. But before I end today's class, let me quickly summarize the difference between spontaneous and stimulated emission. So the spontaneous transitions and the stimulated transitions. In case of the spontaneous transition, this process of emission of radiation via the transition of an electron, atom or molecule ion from the excited state to the ground state naturally, without the influence of any external stimulus, is called spontaneous emission. But in this case, we need stimulus. so stimulated emission of radiation is the process where the emission of radiation takes place in the influence of a photon, and two photons are thus produced from one, and the emitted photons have the exact phase, frequency, polarization and direction of propagation as that of the parent photon. The phenomenon of spontaneous emission is used in ordinary light source such as a lamp, LED, fluorescent tube, and is the key process in laser sources. Now we'll discuss on condition that for achieving dominant stimulated emissions, N2 has to be greater than N1. This condition is called condition of population inversion, which is not essential for spontaneous emission to be dominant, but here for the laser sources, here the stimulated emission to dominate, and population inversion condition is essential. And obviously here no external stimulus is required, external stimulus is required. Also the rate of transition is N2A21, here N2U omega B21. So these are the differences between these two processes. So that's what we have done. We have calculated, written down the rate of the three different processes: spontaneous emissions, absorption, and stimulated emission. We try to understand that to achieve, what are the things required to achieve dominant stimulated emission over absorption and spontaneous emission. We understand that R1 has to be less than 1 and R2 has to be greater than 1, and which is not under normal situations, under ordinary materials, that this does not happen. R1 become greater than 1 and R2 become, so we get dominant spontaneous emission. Now in the next class we will be discussing further on the condition of population inversion. Now what is essential again further to achieve population inversion condition? We understand that is essential, but how to achieve that? What we need? So what type of material we need? So those things we'll be discussing in the next class. Okay. So if you have any questions, I can discuss, or I'll go for taking your attendance for today's class. Any questions from your side?